Now we'll turn our attention to, instead of looking at trig functions defined from a unit circle perspective, we're going to look specifically at trig functions for right triangles. So what we want to think about first is, if we have a right triangle, let's say this is our right angle. Let's call this angle theta. And let's label these sides A, B, and C. Usually we use for the hypotenuse. Notice that in a right triangle, the non-right angles are acute. So we're only going to be looking at this theta can never be more than 90 degrees. It always has to be less than 90 degrees. Also remember that for the sides of a right triangle, we know that a squared plus b squared equals c squared. So if we think about setting up a circle, with origin at this corner, if we label this point, the x-coordinate of that point would be A, the same as the base of that triangle, and the y-coordinate of that point would be B, the same as the height of that triangle. So we notice that that point is on a circle of radius C. So we can use what we'd had before for our sine and cosine and tangent, and the others as well, cosecant, secant, and cotangent. For this particular circle and that point AB, if the circle is not radius 1, we took the y-coordinate divided by the radius. So in this case, that would be the y-coordinate is B, the radius is C. And what we want to notice is, relative to this angle theta, B is what we call the opposite side, and C is the hypotenuse of that triangle. So we'd say the opposite side divided by the hypotenuse would be the same as the sine of that angle theta. And the cosine from this point on that circle, we take the x-coordinate, which would be A, the base of the triangle, divided by the radius of the circle, which is, in this case, the hypotenuse, which is C. And so what we're actually doing is the adjacent side to that angle theta divided by the hypotenuse. So you might, if you've learned trig functions before, this is probably what you learned, that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. So what we're doing here is making a connection between what you might have learned maybe in high school about trigonometry to what we were just learning in chapter 6 about how to use the unit circle to define the trig functions. Tangent of theta from the unit circle approach was the y-coordinate divided by the x-coordinate. So in this case, that would be B divided by A. And in terms of the triangle sides, that's the opposite over the adjacent. Cosecant is the radius divided by the y-coordinate, so C divided by B. And notice, well, that's just the hypotenuse divided by the opposite side, and that's the reciprocal of the sine. Secant is the radius divided by the x-coordinate, which is the hypotenuse divided by the adjacent, and that's the reciprocal of cosine. And cotangent is the x-coordinate divided by the y-coordinate, which is the adjacent divided by the opposite side, and that's the reciprocal of tangent. So the relationships between sine and cosecant and cosine and secant and tangent and cotangent are the same as they were when we talked about trig functions in chapter 6. One thing that is sort of helpful, you may have learned this at some point, is this acronym or mnemonic SOHCAHTOA. So this is the sine function is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. The tangent is the opposite over the adjacent. So you can see sine, opposite, hypotenuse, cosine, adjacent, hypotenuse, oops. Adjacent, hypotenuse, tangent, opposite, adjacent. And then you can remember the others because the cosecant is just the reciprocal of sine, secant is the reciprocal of cosine, cotangent is the reciprocal of tangent. So if you want to use this mnemonic, that's fine if it helps you remember what pieces you need to put together for each of the trig functions. So that's how the trig functions are defined for right triangles. So now, if we have a triangle that looks like this, if it's a right triangle here, we want to find the 6 trig functions of the angle shown. So we say, well, sine of theta is going to be the opposite over the hypotenuse. Cosine of theta is going to be the adjacent over the hypotenuse. Tangent of theta will be the opposite side over the adjacent side lengths. And then the rest will be the reciprocals of those. This 7, that's the longest side, so that's the hypotenuse. This 2 would be opposite of the angle theta. And what we need to know is what's the adjacent side length. So anytime we're missing a side on a right triangle, we'll use Pythagorean theorem. That's not the hypotenuse, so we could call it a if we want to. So we have a squared plus b squared, which would be 2 squared, equals c squared, which would be 7 squared. So a squared would be 49 minus 4, which is 45. So a would be square root of 45. We can clean that up. There's a factor of 9 in there, so 3 times the square root of 5. Since it says exact value, we don't want to round it all, so we'll leave that square root of 5 in there. So we've got opposite is 2, hypotenuse is 7. So the sine of theta is 2/7. One thing you always want to check is that the sine and the cosine values are less than 1, because we know that the range of those functions is just -1 to 1, and because this angle is acute, we know that it should be a positive value. Cosine of theta, we want the adjacent, so 3 square root of 5 over the hypotenuse, which is 7. And then for tangent, we want the opposite, 2, over the adjacent, 3 square root of 5. And of course, we'll rationalize that, multiply by the square root of 5 over the square root of 5. So we'll have 2 times the square root of 5 over 3 times 5 is 15. Once we've got those 3, the rest are just flipping them over. So cosecant of theta is 7/2, the reciprocal of sine. Secant of theta is the reciprocal of cosine, so we'd flip this over and rationalize, of course. So 7 times the square root of 5 over 15. And then the last one, cotangent of theta. If we look at what we had at the start, 3 times the square root of 5 over 2 it would be if we flip that over. So I'm taking the 2 over 3 squared root of 5 that we had written down and just flip that over. It would be the same if you took as if we took our final answer and rationalized it and then reduced. That would work too. The next thing we need to do is talk about what are called complementary angles. And that's just a definition you may or may not remember from geometry. Two angles are called complementary if their sum is 90 degrees or pi over 2 radians. And what you want to notice is that the two angles, the two non-right angles in a right triangle are complementary. Because if you have a right triangle, we have this angle A and this angle B, and this is 90 degrees. We've got A plus B plus 90 would have to be 180. So we can see those two angles added together have to be 90 degrees. All right. So if you notice with that same triangle, if we've got A, B, C for the labels of the sides, for example, the cosine of angle A would be side B divided by the hypotenuse, so the adjacent side divided by the hypotenuse. So cosine of angle A would be B divided by C. But if we look at that from angle B's perspective, that's the opposite side from angle B divided by the hypotenuse. So that would be the sine of angle B. So this next theorem says that cofunctions of complementary angles are equal. That just means that, like in this example, cosine and sine are called cofunctions. And A and B are complementary. So that means that if we use those angles A and B that are complementary, put cosine on one and sine on the other, those are going to be the same value. So similarly, if I look at sine of A, that would be the opposite from angle A. So side little a divided by the hypotenuse. And from angle B's perspective, we'd say, wait, that's just the cosine of angle B. So complementary angles, A and B, and cofunctions, sine and cosine, they should give us the same thing. So for example, cotangent of 23 degrees should be the same as the tangent of 90 minus 23. So what would that be, 67? So if we take any two angles that add up to 90 and apply the pair of cofunctions to them, they should be the same thing. Or secant of 42 degrees should be the same as cosecant of whatever 90 minus 42 is 48. Grab your calculator and just take a look and double check that that's correct. So we want to be in degree mode. Actually, I'll just leave it in radian mode and put in the degrees manually. So try that again. All right. So tangent of 67 is the easy one to type. 67 degrees. And cotangent, we want to do 1 over the tangent of 23 degrees. Try that again. And we want these to be the same thing. Looks good. Secant, 1 over the cosine, so let's do 1 over cosine of 42 degrees. And compare that with cosecant, which would be 1 over the sine of 48 degrees. Again, they are the same thing, right? So, cofunctions have co in the title of the pair, right? So, sine and cosine, and tangent and cotangent. And secant and cosecant. So those are the cofunction pairs. And if you put complementary angles in to the different functions in that pair, you should get the same value. That's what this theorem says. So we should be able to use that idea to simplify some of these values. So if I have tangent of 12 minus cotangent of 78 degrees, what we want to notice is that tangent and cotangent are cofunctions, and 12 degrees plus 78 degrees is 90 degrees. So tangent of 12 is the same as cotangent of 78. So we could say this is the same as tangent of 12 minus tangent of 12. We could replace cotangent of 78 with tangent of 12, and so we can see, well, we just get 0. Those are the same thing. Right? All right, so here, this isn't quite the same, right? Because we have not tangent and cosecant aren't cofunctions. Tangent and cotangent are cofunctions, but tangent and cosecant aren't. But you can notice here we've got some things that are squared and added together. We want to think about the Pythagorean identities. It's been a while since we talked about those, but the one we remember, hopefully, is that sine squared of any angle plus cosine squared of any angle is 1. And we've got a tangent squared involved here. So if we want to get a tangent, we could divide this all by, let's see, what, cosine squared? And we can get the one involving tangent. So one plus tangent of any angle squared is the same as secant of that angle squared. So we can replace this piece with secant of 5 degrees, keep the angle the same, squared. And now we've got a pair of cofunctions at least, and we have complementary angles. So we know that the secant of 5 degrees is the same as the cosecant of 85 degrees because we've got cofunctions and complementary angles. So this is the same as secant of 5 degrees squared minus, we could replace that cosecant of 85 with secant of 5. And so we should get 0 for that one as well. Okay, so back to solving some right triangles. When we say solve a right triangle, that just means find all the sides and all the angles. So let's see, for this one we've got one angle B is 10 degrees. This angle is 90 degrees, we know that, and so we need angle A, and if we've got two angles, we just take 180 degrees minus the sum of the other two. So that's 180 minus 100, so it looks like 80 degrees would be left for angle A. And for the sides, we know, let's see, that side B is 4 degrees, or sorry, 4 units. Let's see, what can we do here? I was hesitating because we haven't talked about inverse trigonometric functions yet, but it's time to talk about them. We'll cover them in more detail in chapter 7, but we'll use this idea here as well since we're doing chapter 8 ahead of chapter 7. So to get the missing sides here, we're going to set up one of the trig functions. So for example, if I could say that sine of that angle B should be the opposite of that angle divided by the hypotenuse. The opposite side is 4 and the hypotenuse is C, and we don't know what C is, but angle B is 10 degrees. So let's see, we could say sine of 10 degrees is 4 divided by C, and if we solve that for C, we'd have C is 4 divided by sine of 10 degrees. Alright, so then we'd grab our calculators, and we need to put in 4 divided by sine of 10 degrees, and I'll just put degrees in manually since I'm not in that mode. So 23.04 if we round to 2 decimal places. And when we have two sides, so now we have side C and we have side B, now I use Pythagorean theorem to get the third side, which is not the hypotenuse, so we would use a squared plus b squared equals c squared. We don't know a at this point. B was 4, so 16, and this is 23.04 squared. So a squared, grab your calculator again, 23.04 squared minus 16, 514.8416, and then we'd want to do the square root of that. And we'd get 22.69. Oops. $22.69 for A. Alright, so let's see. The key things we used here was that the sum of the angles has to be 180 degrees, and the sides have to satisfy a Pythagorean theorem because we know we're talking about a right triangle. And then we wanted to use a trig function at some point to get the side we didn't know, one of the two sides we didn't know. So if two sides are missing, use a trig function to find one of them. So at this point, when we said the sine of b is the opposite over the hypotenuse, we needed to use either the sine or the tangent because the side we knew was the opposite. So if we're going to pick on angle B, we'd say, well, we have the opposite, so we either need to use sine because that's opposite of hypotenuse, or we would need to use tangent because that's opposite over adjacent. We could have also looked at angle A, but if we were going to look at angle A, then we would need something that involved the adjacent, right? So the side that was given is opposite of angle B and adjacent to angle A. So the trig function we choose depends on how the side that's known is related to the angle we're using. So we could have, if we wanted to, we could have said, for example, cosine of angle A, which would be the adjacent over the hypotenuse, was 4 over c. We could have looked at it that way too, and that would have been the same. So cosine of 80 degrees is 4 over c, and we would have said, well, then c is 4 divided by cosine of 80 degrees. It would have led us to the same point. So there's not a rule about which trig function you need to use. You just need to use one that involves the side that's known. So let's see, this is just an aside that we could have done in place of that where we did sine B. Okay, another one. So the convention is when you're labeling sides of this triangle that the angles are capital letters, and they use A and B for the acute angles, and if we want to use capital C for that right angle, and the side opposite the angle has the same letter but lowercase. So little b would be across from angle B, little a would be across from angle A, and little c would be across from angle C. So when we were told to solve this triangle, we need all of the angles and all of the sides. So what's given here is that angle A is 20 degrees and side B is 6. It's also given that angle C is 90 degrees. So we can find angle B pretty easily. We take away the sum of the other two. So 180 minus 110, that would be 70. So angle B we know, and now we're just down to the sides. And the side we know is this one, that B is 6. So if we want to pick on, let's say, angle A, B is adjacent to A, so we would want to say use maybe the cosine function or the tangent function, something that involves the adjacent. Let's do tangent this time. So the tangent of angle A would be the opposite over the adjacent. The opposite is side A. The adjacent is side B, which is 6. So since we know angle A is 20, we'd have tangent of 20 degrees is A divided by 6, which means A is going to be 6 times the tangent of 20 degrees. Grab a calculator. 6 times the tangent of 20 degrees. 2.18 if we round to the nearest hundredth. And that's a side length. And now for the last side, we'll use Pythagorean theorem. A squared, 2.18 squared. B squared is 6 squared. And then we'd grab a calculator, add those together and take the square roots. So 2.18 squared plus 36. Take the square root of that. Oops. Point, or 6.38 if we round to the nearest hundredth. So we were able to find all the sides and all the angles. And again, just using the tools we had from the first example. And again, the complicated step is where you're using a trig function to get one of the sides. And that we said we could have used angle B, but we just arbitrarily chose to use angle A, and we noticed that we had the adjacent side. So one of the trig functions involving the adjacent side is what we needed to use. All right. Then the next one, we've got 2 side lengths given instead of any angle measurements. So let's draw our triangle. Got a 90-degree angle. The way this is drawn, 5 should be the longer side, so this is my A, and 3 would be the shorter side, so I'm going to label that one B. C we don't know, but we can get it from the Pythagorean theorem because we have 2 sides. So we've got 25 plus 9 is C squared. Looks like C would be the square root of 34. All right. Then this would be angle A, this would be angle B, and it's trickier when we don't know the angles. We'll still write down a trig function. For example, we can say, if we're trying to find angle A first, we have all the sides, so I'm going to pick on cosine. So I'd say that cosine of angle A is the adjacent divided by the hypotenuse, which in this case is 3 divided by square root of 34. So if I've got, let's just write this again, cosine of A is 3 over the square root of 34. What I want to do is figure out what A is, and what I have to do is use an inverse function. So to solve for A, we would say A is the inverse cosine of 3 over the square root of 34. And now that's the button on our calculator that has that, what we've talked about, looks like a -1 exponent. That's the inverse cosine function. So if a cosine value is given, it will tell us the angle between 0 and pi having that cosine value. So if we want to figure out what A is, we would do inverse cosine of 3 over the square root of 34. And because I'm in radian mode, that's actually a radian answer. So we want to get degrees. Is there a convert to degrees? That will give us degrees, minutes, and seconds. So let's talk about that. So close to 1 degree. Let's see. Let's do better than that. Let's just go to, instead of switching, let's just be in degree mode, as we know we want degrees for our answer. So when you're working with these right triangles, probably the best thing is to be in degree mode. Then you don't have to worry about it. So let's try that again. Let's do inverse cosine of 3 divided by square root of 34. So 59.03 degrees should be our answer. So just to, when I did the convert to degrees, minutes, seconds, what it was doing was taking what it thought was a degree answer and converting it into smaller pieces. So don't worry about that. But the best thing to do when you're doing these inverse trig functions for right triangles is make sure you're in degree mode, and then the answer that it gives you would be in degrees rather than in radians. So we know what angle A is, and we use this new idea that if we have a trig function known for a given angle, but we need to find that angle, we can use what's called the inverse trig function that gives us the angle if we know the cosine value or the sine value. Then finally, let's see, we need to know that last side. We don't want to do what we just did again. That was more work than we want to do if we don't have to. To get that last angle, that's the only thing missing. We'll do 180 degrees minus 90 plus 59.03. Or this is always going to be the same as just 90 minus 59.03. That works too. Looks like 30.97 degrees for that last one. So we know all the angles and all the sides. A little more complicated. And then a couple of word problems. There's probably a picture of this in your textbook, but it's good practice to be able to read the description and come up with your own picture as well. So number 52 says a person in a boat offshore from a vertical cliff whose height is known, 100 feet, takes a sighting off the top of the cliff. If the angle of elevation is found to be 25 degrees, how far offshore is the boat? And I said it takes a sighting off the top of the cliff, but they took a sighting of the top of the cliff. That's a little different. So one new word here is angle of elevation. That's always measured from the horizontal line of sight upward. So if we make a little sketch here, we've got this vertical cliff, that's 100 feet. And this person is in a little boat. And we measure from the line of sight upward, and we get 25 degrees for that angle. We want to know how far are we offshore. So the cliff is at the shoreline. So we want to know that distance. Let's call that x. Now let's call it a letter, since we're always using letters for the sides of triangles. Let's call it A. Notice that relative to the angle 25, A is the adjacent side, and this is the opposite side, right? So we don't have the hypotenuse, otherwise we could just use the Pythagorean theorem. We have an angle, we have the opposite side, and we want the adjacent side. If we're looking at the opposite and the adjacent sides, tangent is the function that pulls all that stuff together, right? So we would say tangent of 25 degrees is the opposite, which is 100 feet, divided by the adjacent, which we don't know, but we've called A. Tangent of 25 degrees is something we can get from our calculator, so we'd say if I solve this for A is 100 divided by tangent of 25 degrees. And approximately oops. I'm in degree mode now, so I don't need to put degrees on there. 214.45 feet from shore. So we'd say the person is about 214.45 feet from shore. So the key was to think about what's the angle that's given and what sides do we have relative to that angle. We could have done more work. We could have said, well, I know this is 90, so I could figure out this angle up here, and then I could use that angle instead, but we want to keep it as simple as we can. So let's use the tangent for the angle that's given. Not so much work. Okay, another word problem. Security camera in a bank is mounted on a wall 9 feet above the floor. And this one is talking about an angle of depression. So let's talk about that phrase also. That's also is measured from, it's measured downward from the line of sight. So if we've got, here's our wall, here's where it's mounted, 9 feet above the floor. We want the angle of depression, which is measured from that downward. So we want that angle. And it's supposed to be directed at a spot 6 feet above the floor and 12 feet from the wall. So let's see, 12 feet from the wall. We want this to be 12. 6 feet above the floor. Let's see, my drawing's not so great here. Let's try again. So 12 feet from the wall. 6 feet above the floor. Okay, put in some pieces here. That's a little better. We still want that angle. This would also be 12 feet, right? This piece here would be 3 feet. And that angle would be 90 degrees. We also know that since these two dotted sides are parallel, this angle is the same as the one we're looking for, right? But we could still make just some more triangles. This side would be 3 feet, right? This side up here would be 12 feet. And if this angle is A, the one we're looking for, again, we have what's the opposite side and the adjacent side for that angle A. So we could use the tangent function again, right? So we could say the tangent of A that we don't know is the opposite, 3, divided by the adjacent, which is 12. And then again, we don't know the angle, but we know its tangent value. That's where we do the inverse tangent function. So not the tangent function itself, but do the inverse to the other side. So just to make that clear, again, basically what we're doing is this. The inverse tangent of the tangent, you know from college algebra that when you do a function and it's inverse, you just get that input back. So that's what we're just getting a on this side. And we're doing the inverse tangent to both sides. So on one side we just get a back, and on the other side we get the inverse tangent of 3/12. Let's figure out what that is. 3/12 is the same as 1/4. So inverse tangent of 0.25. So about 14.04 degrees. So we'd say the angle of depression should be about 14.04 degrees. In example 6 here, we have some more new terminology. We've got this phrase, a bearing of south 80 degrees east and a speed of 15 knots. We'll talk about the bearing in a second, but 15 knots just means 15 miles per hour, basically nautical miles per hour. So let's sketch a picture here. We've got the Port of Miami. We'll call that M for Miami. Let's say a ship is leaving, not a shop. So a ship leaves that port with a bearing of south 80 degrees east. So what that's saying is we're going 80 degrees east of south. So it's going to be actually something like this. So from east, we would be like 10 degrees south of there. So in south, but then 80 degrees east from that. So I'm just going to sketch that in roughly. We'll use that more carefully at the end of the problem. But let's just draw this in kind of arbitrarily. And it's saying they're going a speed of 15 knots. And then in 1 hour, the ship turns 90 degrees. So at some point here, we've gone 15 miles because it's saying the speed is 15 miles per hour and we're going for an hour. So 15 miles, turns 90 degrees towards the south. So and now we're headed this direction, and this would be a right angle. Right? So here's where we've got a right triangle coming in. We're doing 2 hours at that same speed in this direction. That means this side is going to be 30 miles. And we want to know what's the bearing to the ship from port. So here's where the ship lands. We've got this triangle here. And we can figure out this angle. Let's call it angle A. And then once we have that angle, we'll be able to talk about, well, what is the bearing associated with that angle. Right? So we've got basically that the tangent of A, because we've got the opposite and adjacent, we want to pick on tangent. So here's adjacent, here's the opposite. The tangent of A is 30 over 15, which is just 2. So A, if we want to solve that, again, we'll use the inverse tangent function. So our calculator is all set in degree mode, so our answer is going to be in degrees. So A is the inverse tangent of 2. So 63.43 degrees, we'll say. So 63.43 degrees. So we had already figured out that this angle up here, just from what was given in the problem, if this is east, that's 10 degrees. So if this is straight south, this angle here would be the 90 degrees minus 73.43. So if we do that subtraction, we get 16.57 degrees. So we would say the bearing of the ship from port is south 16.57 degrees east. Because we're not quite going straight south, we're going 16.57 degrees east of straight south. All right, then a couple more examples here. These word problems can be tricky, so I wanted to get enough examples that you can get through the problems on the exam and in the homework. So we've got Sears Tower in Chicago is the third tallest building, and it's topped by a high antenna. So we've got a surveyor on the ground makes the following measurement. So surveyor here, building, and then antenna on top of the building. This drawing won't be scaled correctly, but angle of elevation to the top of the building, so from the line of sight to the top of the building, 34 degrees. His position, the measurement from his position to the top of the building is 2593 feet. And from his position to the top of the antenna is further, 2743. Okay, so the first question is how far away from the base of the building is the surveyor located? So first we want to find this side, let's call that A. Notice that that's adjacent to that angle, 34 degrees that we know. And we also have the hypotenuse of this right triangle. So we could pick on adjacent hypotenuse, we'd want to use cosine. So we'd say cosine of that angle, 34 degrees, is the adjacent side, A, that we don't know, divided by the hypotenuse, 2593, which is telling us then that A would be 2593 times the cosine of 34 degrees. Grab your calculator. 2593 times the cosine of 34 degrees. I'm in degree mode, so that should be right, 2149.69. feet. So I'll put that in here. Now we have two sides of this triangle associated with one side being the height of the building. So we could use Pythagorean theorem. So let's call this height B for building. So we'd have 2149.69 squared plus B squared equals 2593 squared. So B would be approximately the square root of 2593 squared minus 2149.69 squared. And we need a calculator for that. Take the square root. 14 looks like 1450 if we round to the nearest hundredth. So the building is 1,450 feet. Then the next question is asking what's the angle of elevation from the surveyor to the top of the antenna. So if we look at this larger rectangle or triangle, excuse me, we now have two sides of that triangle, so we should be able to find, let's call that angle C, since that's part C that we're on. So we've got the adjacent side and the hypotenuse again. So adjacent hypotenuse, we'd want to use cosine. So cosine of C would be the adjacent 2149.69 divided by the hypotenuse 2743, which means C would be the inverse cosine of that ratio. Again, when we're looking for the angle and we have the cosine value, we want to do inverse cosine to get to the angle itself. And we're in degree mode, so our answer is going to come out in degrees. So inverse cosine of 2149.69 divided by 2743 gives us 38.4. That makes sense. It should be larger than the original angle just measuring to the top of the building, but not significantly larger. And then if that is 38.4 degrees, we could figure out the longest side, including the building and the antenna. So if we call that H, we've got this angle here, C is about 38.4. So we could say, well, we're looking for the opposite side, and we have the adjacent side, or we have the hypotenuse. We could pick on either one. Let's use the opposite side and the hypotenuse. Then we'd want the sine function. So we could say sine of 38.4 is H over 2743. If we want to know the height of the antenna, we don't want that whole height, but we could at least, if we know this whole height, subtract the 1450 to get the height of the antenna. So let's determine that entire height first, since that's the side of the triangle, and then we'll use that to figure out the antenna. So we'll take H minus B eventually, but we can figure out H this way. So H would be 2743 times the sine of 38.4 degrees. We need a calculator for that. Looks like 1703.8. So H minus B is 1703.8 minus 1450. $253.8. So So that would be the height of the antenna. Okay, one more problem, and this one's definitely the trickiest one. So we've got this person in an hot air balloon and wants to figure out how high he is. So let's say here's our, I can draw a better hot air balloon than that. Hot air balloon. Don't know the height. But choosing a landmark over here to measure and figures out that the angle of depression to that landmark is 54 degrees. So remember, the angle of depression is measured from the horizontal downward. So this is 54 degrees. And again, here's the thing we're trying to figure out. Let's call that x. Travels a little further to the east, 100 feet. Measures again to that same landmark. Imagine that's a straight line. We've got then that this angle is 61 degrees. It makes sense that it would be a little bit steeper since we're hopefully closer to that landmark, right? And that's supposed to be enough information to determine the height of the balloon. So we don't have a whole lot here, but we want to be looking for right triangles. So if we've got this at least as a right angle, we've got two different right triangles we could be looking at. The height is involved on both of them. It's the same, but the angles are different for those different triangles, right? So, and we don't have any complete sides of any of those triangles. So let's do this. Let's call this side y, since we don't know that, but at least we have 100 for part of one of these triangles. So we're going to need to set up a system of equations, actually. For each of these angles, we have at least close to the tangent values. We've got almost the adjacent, and we want to know the opposite side. We don't really care about the hypotenuse in any of these. So we could say, let's see, with the way we've labeled things, we could say the tangent for 54 degrees would be x divided by 100 plus y. And the tangent for 61 degrees would be x divided by y. And we want to solve for x. That's the thing we want to know, right? So we could solve one of these expressions for y and substitute it into the other one. Probably the easiest one to solve for y would be right here. We could say y would be x divided by a tangent of 61. So we could solve that for y and then substitute that in here. So then we could have tangent of 54 degrees is x divided by 100 plus x divided by tangent of 61 degrees. It's a mess, but it's something we can solve because it just has one variable. If we multiply on both sides by this denominator, we'd have tangent of 54 degrees times 100 plus x over tangent of 61 equals x. We have x on both sides, so we can't stop there. We still need to keep going. So we could distribute, I suppose. 100 times tangent of 54 degrees plus x times tangent of 54 degrees over tangent of 61. is x. Now we want to get the x terms on the same side. So we could do 100 tangent of 54 degrees equals x minus x times tangent of 54 over tangent of 61. Then if we're trying to solve for x, we'd want to factor that x out. So we'd have 1 minus tangent 54 degrees over tangent of 61 degrees. And we're almost there. We could divide both sides by 1 minus tangent of 54 over tangent of 61. Let's get an approximation for that. So 1 minus tangent of 54 divided by tangent of 61. So that's about 0.237. So we've got x is about 100 times tangent of 54 divided by 0.237. Let's see if it seems reasonable. $580.75. feet for that balloon. Yeah, it's hard to know with that much information. It seems like it's a reasonable height. Yeah, so like I said, in most cases in the book, they're going to give you the picture. I just want to give you some practice with interpreting the words and getting the symbol or the picture to match up with what they're saying.